be here. As a chemist, I don't want to bother too much with chemistry, as you will see, but it's the opportunity for me to have the contact with people from another discipline and a totally different, let's say, perspective about the problems I'm interested in. And so I accepted really immediately the invitation of Axel and Raphael to come to Sweden to discuss, in fact, about such aspects. So more than giving really a talk dealing with chemistry, because I don't think it's relevant somehow, what I want to convey, as it was said by Axel, is a sort of chemical perspective on chemistry and where we are in relation somehow to biology. And it's what I intend to illustrate during my talk. The title is here. We will start from chemical simplicity, which is basically, for me, what I know in chemistry, to biological complexity in the sense biology with this word complexity, whatever you put behind. And instead of speaking, what I would like to do is to be able, not at the end of the talk, but at the end of my stay here, to draw some framework in order to define a research program, which is to act. What I will try to say is that you can think, but it's much more difficult to act. And the chemists are people generally that really act in preparing, fabricating things. So this is the idea basically. So what is a chemist? The chemist is basically a sort of physicist, but it's a physicist with some special knowledge about molecules. The type of knowledge we have is the following. If I draw a molecule on the blackboard, here on the whiteboard, a chemist will immediately see what we are discussing about in terms of solubility, stability, reactivity, whatever. For a physicist, except if he's trained a lot in chemistry, it's a drawing and no more very often. And there is another difference very often. It's that I like to discuss with matter as a chemist, so in that case with molecules. That will be my level, which is very restricted from that point of view. But I want to act. If you give me some molecules, what I want to do with those molecules is something over as much as I can. So, in relation to this crude picture about what a chemist is, let's just have a look now at the border between chemistry and biology, which is of interest for me. So, when you learn about biology as a chemist, generally this is associated to biochemistry, and you will open a textbook and you will see such things. You will have molecules, in that case ATP, ADP. You will have other molecules that are quite big, let's say proteins, for instance, and you will see organizations. And we are said that all this stuff is basically chemistry. Chemistry is everywhere, and so on and so forth. But at the very end, we don't know exactly what is the link between, let's say, really chemistry, the molecules, the reactivity, and the organization in biology. So what can be said is basically that we have spatial scales that are given here. So this is the easy way, let's say, to see an evolution from the nanometer scale of molecules, the so-called supramolecules, bigger, associated to, let's say, larger molecules or assemblies of molecules, and then organizations. And the characteristic spatial scale for those organizations is typically the cellular scale, 1 to 10 micrometer. What is interesting also is to have a look on, let's say, time scales. And in chemistry, the time scales are the following. Typically, molecular motion is the picosecond regime, and the chemical reactions can be very, very slow. So you have a broad range of rate constants. And in relation to biology, the typical rate constants we are interested in are probably much more restricted. But you have typically the growth of an individual, and then you have molecular events in cell taking place, let's say, from millisecond to typically an hour, something like that. So you have sizes, you have times, and all is entangled when we deal with biology in chemical terms. So what I want to do right now is just to summarize 200 years of modern chemistry, just to tell you where we are with the knowledge we have to understand and to act. So, intramolecular assembly means, are we able to build molecules from atoms? And you will see the answer is yes. So it's typically related to the interaction between atoms with Morse curves like that. And what are the remarks we can make and how important basically they are? Energies of bonds, and so energy barriers to transform a molecule in another one, are typically in the 1 to 10 electron volt range. So there are large energies. Bonds between atoms only affect their surface, not the core of the atom. And what we can say is that on Earth, at least, temperature does not affect what the atoms are and what the molecules are. You see that the energies of the bonds are much above kT, which means that basically due to these observations, we can rationalize the formation of molecules in terms of very local environments, essentially atoms, or sometimes functional groups, but a few entities to understand the rules of assembly in a molecule. So basically it's very easy. There is no such coupling that when you have two atoms, you cannot recognize two atoms of oxygen, you cannot recognize anymore an oxygen in the molecule. So you have the repertoire of the periodic table, which is very limited, and basically with those rules, you can quite easily predict after 200 years of history how the molecules are assembled and why they're assembled that way. And just to give you an example of the, let's say, sophistication we achieved in chemistry, so this is the starting point, the synthesis of urea by Friedrich Wöhler, so about 200 years ago. And just before my PhD, the synthesis of the palytoxin was reported by Kishi in Harvard. So don't pay attention to the atoms, but maybe you have that in your memory when you were young students. Each time you have, for instance, this type of center, you have two possibilities of relative orientation for the OH. And if I try to evaluate the number of so-called stereoisomers of this molecule, you have more stereoisomers of this molecule than the number of stars in the universe. And at the moment, in '87, Kishi and his group was able to synthesize only one star, this one. So that it's simply to show that really we master matter at that scale.
Does that say anything about anything more? I mean, because it tells me something about the free energy landscape of those possibilities. If there's that as many as there are stars in the universe, then there must be something about this configuration. It can't just be pulled out of the Boltzmann distribution.
No, it's simply to say that you have a man who really predicted the pathway by starting from elementary molecules to reach this one after maybe 100 steps of synthesis. It's not, let's say, to mix all the things together and by some funneling events you will reach only one molecule. It would be very nice if the story would be that way. No, it's years and years of work for 50 persons in the group. But still, even with this work, in some fields, you will work and you don't obtain anything. Here, with the rules I expressed before, very crudely, you can expect to obtain such a molecule. So at the larger spatial scale, you will start to deal with assemblies between molecules. So it's very close to what I expressed before, except that instead of having atoms here, you have molecules. The type of behavior is exactly the same, but with some differences. And the main differences here are connected to the energy, let's say, associated to the bond. It's now an intermolecular bond, which is associated to energies in the range 2 to 20 kT, typically, so much smaller than in the case of intramolecular bonds. In addition, molecules are flexible, and I give you here the example of ethane. In ethane, you have an angle between this bond CH and CH. And the potential energy of a system varies as a function of this angle. And you see that the amplitude of the variation is typically 10 to 20 kilojoule per mole, so which is basically, let's say, KT is 2.5 or 3, it will be maybe 4 KT, something like that. And here it's simply logarithm of x to say that the mixing entropy is a term that you cannot neglect, let's say, at the energy associated to such an interaction. That is that all basically terms here, molecular interaction, deformation of molecules, and mixing entropy, will have typically the same order of magnitude. What that means? That means essentially that I cannot consider anymore a very local environment to analyze the interaction between molecules, because a molecule can rearrange itself when it starts to interact with another. I have to consider it as a flexible thing, and so the analysis for the prediction is not as local as when I deal with intramolecular bonds. Another aspect which is important is that temperature now can play a role. If I change the temperature simply due to this value, I can considerably affect the type of interaction between molecules, and in particular, I will have to introduce phase diagrams, an idea which doesn't belong to molecular chemistry as itself. I have now, as a function of the parameters, concentration, temperature, I can expect to obtain different types of assemblies. So it's already more difficult, but still, again, it's possible, typically from the 70s, to obtain structures as complicated, I would say, in terms of structures as, for instance, hemoglobin here, which is made of 4 different proteins that are assembled in a heterotetramer here. And here you have a system which is as big, which is built with another strategy by assembly of molecules and ions, but the typical size of what can be obtained at the present time in chemistry satisfactorily compares with the size of let's say, such a tetramer. So basically, even if it's more difficult, chemists have worked for typically 30 to 40 years and devised rules in order to be able to obtain such systems. So now we face the scale I showed, which is typically 1 micrometer, and that I called molecular systems assembly. Is it possible, with the tools we have in chemistry at the moment, to design a system that could look like a cell, for instance? And from that point of view, I separate the design in 2 parts. I will consider first what I call self-assembly, but based on thermodynamics. That is a sort of extension from what I introduced just before. That is to start from supramolecular chemistry to more organized molecular systems at a larger scale. In that case, the goal will be a structure. It can be a fiber, a crystal, for instance, that typically belong to this story. And in fact, even if we cannot predict at the moment the crystal structure from the structure of a molecule, we can say that all that story was largely explored and is reasonably understood at the moment. So where is, I would say, the border, the crucial border for chemistry at the moment? It's definitively here. It's, if we start to speak about self-assembly from kinetics, I don't know whether that could correspond to complexity, but I decided to use it here. Why is it, let's say, a border which is important? It's precisely because we have not, as chemists, the rules to design such systems. And one reason is that the conceptual corpus that could be used to design a system based on, let's say, kinetics in that way, at that scale, should belong to the field of dynamical systems. And I don't know what is the situation in Sweden, but at least in France, when you are a chemist, you are not taught dynamical systems, they more belong to physics than chemistry, and are taught quite late in the studies. So chemists are not prepared conceptually, intellectually also, I don't know, really to deal with dynamical systems. The goal is not something that we like in chemistry. It's not a molecule, it's not a structure. It will be probably a dynamical phenomenon. And a dynamical phenomenon is not attractive as such. You prepare drugs, dyes, or whatever in chemistry, but a dynamical phenomenon. Why should I pay a lot of effort to obtain such a phenomenon? In fact, we have only a few investigations in the literature dealing with such things, and you probably know the Belousov-Zavotinsky reaction, which is a big name, but a unique name. Let's say I know only one reaction, its sisters basically, but they all belong to the same group of chemical reactions. They are quite unique. And in fact, many open questions because we don't understand how that works at that scale. So we really need some theoretical input, and it's one reason I'm here, in fact, to discuss, to exchange with people about possible theoretical frames in order to be able to design systems that self-assemble with kinetic constraints. So what I want to express now is for a typical chemist as I am, being trained as a chemist, what is singular in biology from the point of view, in particular, chemical dynamics. And that has to do essentially with the history of chemistry. And I will briefly introduce that later. What is absolutely unusual for a chemist in biology is first the management of free energy. When you are a chemist, you are interested to obtain pure compounds. And that has to do with the fact that we had in the history, especially in the 19th century, to prepare pure compounds in order to be able to analyze them. And analysis was key in that case. And so we have a memory of pure compounds, a sort of trauma, such that we conceive only chemistry as preparing pure compounds. And biology is nothing but a big, big mixture. Typically, your cells, they contain 10 to the power 6 different compounds in a cell. Another aspect, and now that started to change with green chemistry, is the significance of catalysis. Catalysis is the technology of living beings for many aspects, selectivity of chemical reactions, and I will try to convince you that it's very important also for free energy translation. There is another aspect which is totally unusual for chemists, it's the management of timescales. So, what I will show first is that it's possible to control evolution in chemistry by coupling reactive sites. And I will also show that if you can manage to work at a steady state in a system, like in a living being, you will be able to overcome the intrinsic relaxation times of chemistry. And you need to be able to reach such conditions of out of equilibrium at a steady state to be able to write the story of biological evolution. If you consider, let's say, if you accept the idea of biological evolution, you have to deal with 3 billion of years of evolution. And I don't know so many chemical reactions with a characteristic time of 3 billion of years. So there is some trick in order to allow chemistry to continue for 3 billion of years without reaching an equilibrium. And what is this trick?
Sorry, before you go too much farther and before I guess we leave philosophy, are you saying the management of free energy, if you go back to the previous slide, is only relevant to your second bullet, but not...
In relation to what I intend to say, yes.
Oh.
It will become more clear after a few slides.
Just because I would say self-assembly from thermodynamics requires no
free energy is everywhere,
yeah.
Definitively. But when I'm ready to reach the equilibrium, I don't pay so much attention the way I spoil out my free energy. Whereas when I intend to self-assemble by using kinetics, I will have to pay a lot of attention on the mechanism to, let's say, spend out the free energy during the evolution.
And when you said 3 billion years, Where does that time scale come from?
It's biological evolution.
Yeah, but it doesn't have to be that long. It's not clear that it's that long.
Biological evolution? I mean, there is no reason why it's long, but the point is that basically what we are, what I'm, it's, let's say, a few tens of kilograms of aqueous solutions, which is a reactive, let's say, container, that produced another reactive container, possibly with children or whatever, and this continues for 3 billions of years. At the beginning, it was something totally different. But it's a story of containers, you know, reacting, and during 3 billions of years. Whereas the chemical reactions in the system, the time scales have nothing to do with these 3 billions of years.
But would you even say that the time scale for the origin of life could be that long?
No. It depends what you name origins of life,
yes.
But it's simply to say that there is a huge time, and you have other times that are much shorter.
Yeah.
And steady state, from that point of view, being able to maintain out of equilibrium at steady state the system is a key. So, just to explain the idea of, let's say, management of free energy, I hope I will address your point. A total synthesis, it's not to bother you with synthesis, it's just to have a picture in front of you. So this is typically a transformation from an initial reactant, a succession here of steps to obtain here a final product. This is typically what you will find in journals of chemistry, and when you pay attention on what is written on the arrows, you will see here what is the chemical yield. It's the typical yield of each step. And you see it's 51, very poor, 91, very good, 97, even better. And you see that what you try to obtain for each step is essentially 100%. If you are 100%, you are an excellent chemist. But otherwise, this is the look. Now, let's have a look on the metabolism. If you are not very well trained, basically you see exactly the same. You have molecules, you have arrows, and so, again, there is no difference. In fact, you have differences, two main differences. The first one is that you have no yield. This is not relevant, simply. I said before, you are an awful mixture. So you are not visibly interested in mixture, in products as such in biology. And also, these discs, black discs, correspond to enzymes. Each step is catalyzed. Why? So here we can ask questions. Can I compare really what I saw before with this metabolism? So do we synthesize something with a metabolism? Is it a chemical operation? The answer is no, probably. So, to make the things a little bit more clear, I hope, what is the rationale behind our strategy of chemists? It's very simple. We want to obtain a pure compound. Again, this is our, I would say, phantasm somehow. And we will start from a reactant. It will be a multi-step synthesis. And what we want is that for each step, the yield of the product will be 100%. And you are ready to pay, and to pay a lot of free energy to reach that. And it's very simple. If you use some of the reagents with a large free energy, you can expect, for instance, at equilibrium, that you will obtain your intermediate with a good yield. And you don't care whether you will have to pay this large amount of free energy. It's not relevant. And so each step, what you do, you add some free energy in order to displace, let's say, equilibrium toward that point. You add another dose of free energy, and so on and so forth, to obtain a good yield of the product. So we focus on this transformation. We want a good yield. And if I consider now the conversion in terms of free energy, it's very poor. It's very poor. I paid a lot to reach my product. Now, what should be the strategy of biology? There is no strategy. I hope at least that you believe that there is no strategy in biology. But what is the situation in biology? Still, I can write this transformation. But, and I will use also reactants with a large content in free energy, but each step associated to some dissipation of free energy will be coupled with some other event in the system, some other reaction, some other process, such that I will use this energy to perform another operation. And so I never really spend out a lot of free energy for nothing. All is coupled in the system. And so I cannot compare living beings with a plant, with a chemical plant. It's not dedicated to synthesize a product. It's not the goal. In contrast, the overall conversion in Gibbs free energy is very good, and this is fortunate. You don't eat every minute of your life. You can do other things, and it's very important during biological selection, of course. So, if this is true, it's very nice, but now the question is, how do you achieve this? You need a technology in order to transfer free energy from one chemical reaction to something other. And you need to achieve that. So I don't pretend that what I will introduce is unique. Probably many, many strategies are used in biology, because biology had a lot of time during evolution to try all what was possible, basically. But what I want to emphasize on is now the possibilities that are provided by catalysis. So what is catalysis? In the textbooks, you will find this type of drawing. It's the idea that for a chemical reaction, you start from a reactant here. You have to distort somehow bonds in order to form the product. And so you have to pay, and to pay an energy barrier, which is written here. So in the textbook, you will find that a catalyst is something that will, let's say, create a tunnel here in the mountains such that the energy barrier will be low. This is the picture you will find. I hate it, personally. I hate it because, of course, what happens when you add a catalyst is that you totally change the mechanism of the evolution. And so here, the so-called reaction coordinate, which measures somehow the deformation to go from the reactant to the product, now is not one-dimensional. You will increase a lot the number of steps that are involved in the transformation, and you totally change the dimension of the space to analyze the events. So it's not simply a tunnel, it's a change of space. So basically, a catalyst is a system that will allow you to accelerate the process of transforming a reactant into a product simply by changing the mechanism. And this is very, very important, in fact, this idea of kinetic control. Because if I take an egg of alga and an egg of a frog, if I show you those eggs, you won't see the difference. Basically, they eat the same. But at the very end, because the pool of catalyst is totally different, in one case you have a plant, in the other case you have a frog. So it's this idea that basically it's a pool of catalyst, whatever you name it, proteins, DNA, and that stuff, but basically it's a way to change the destiny of matter under kinetic control. So, how is it possible to transduct free energy with catalysis? So I take one example, which is an analogy, an aerodynamic analogy. So now, this is a lock of the 17th century in Manille-les-Hameaux, in France. And I want to convince you that a lock is no more than the assembly of two catalysts. And here, when we look at the way it works, so you all know how a lock works, you see that basically you have a moving wall, and this moving wall is a way to accelerate the transfer of water. It's a sort of catalysis somehow. And you have two, they're assembled close to each other, and they work in a nicely organized way. You know, if you change the way to use the walls, there is no hope to see your boat going downstream to upstream. So you need to have this type of energy source in order to make the transfer from one side to the other side, to have in that case two catalysts, and some kinetic order in order to be able to perform this transduction of free energy. And this is simply to introduce an analogy which I will express in chemical terms later. So the typical picture that was introduced by Manfred Eigen about, let's say, evolution, biological evolution in a formal way is the following. And again, I start from the textbooks in biochemistry. I will discuss about catalysis, Michaelis-Menten catalysis a little bit. Maybe you are not familiar with it. An enzyme is a species that will interact with, let's say, a reagent to give a sort of complex, which is written here, and the complex will then form a product and give back the enzyme. You can generalize this system, and you will find in the textbooks of biochemistry the so-called cycles, biochemical cycles, the citric cycle, for instance, and some others. And on the arrows of those cycles, you will see that you use some ATP or something like that very often. This is the way it's introduced in the textbooks. But again, it's a wrong way, in my view. The way that was introduced by Manfred Eigen in '74 in his book, The Hypercycle, is the following, and I think it's relevant for astrobiology somehow. Imagine that you have a source, a primary source of energy. It can be, for instance, the fact that the solid ground is not in equilibrium with the gas or with water, which is basically the situation in the model of primitive Earth. If you can imagine, and that the spontaneous relaxation of this primary source of free energy is slow, okay? The chemical reaction, the spontaneous one, is slow, and that a molecule or a cycle simply going in that place is able to accelerate this, so it can graft on this primary source of energy, and you will start to make this cycle, let's say, being active and with a rotation and a direction which is forced by the source of energy. And now the situation is the following. If the source is big enough and slow enough somehow for spontaneous relaxation, I can graft many such enzymes or cycles. At their turn, these cycles can be the subject of grafting another cycle, and so on and so forth. So basically, it's this idea. I have a primary source, which can be very oxidation of iron 2 or whatever, and I have chemicals in this area that can start to react that way and give rise to some interesting dynamics, which is typically the model of evolution, very formal but very rich, introduced by Manfred Eigen. So then the idea we can have is typically that biological evolution has to do with a random assembly of, I said, generalized catalysts that will graft on steady state energy sources. And why steady state? In order to have enough time to explore all the possibilities of assemblies. And that continues at the present time, as long as we have free energy sources, either the primary one, which can be typically the sun at the moment, and then other possibilities of secondary, tertiary free energy sources. And we still explore this. So a very important point in relation to this idea of assembly. You want
Excuse me, before you go on, are you going to address the issue of how the slow variable maintains its steady state while it's getting drawn?
I won't treat really this problem, because I have some ideas, but it's not so simple. It's not formalized, at least for me, totally. So in relation to this random assembly and coupling, there is one idea I think to be quite important. It's the idea of overcoming, let's say, the range of physical interactions. So typically when you have two parts in a molecule, they interact with each other, let's say, by electromagnetic interaction, for instance, and the typical range in water, since it will be screened, for instance, for ion-ion interaction, will be 1 nanometer. If I want to have the coupling I introduced before that will change the interaction between those sides, you see that in 1 nanometer I have not a lot of place to introduce some perturbation. And so typically, for instance, in that molecule there is an interaction between those sides, and the proton exchange properties are different from the ones here because the distance is larger, but at that distance I can consider this position and these positions are as independent, typically. And so basically the way to modulate here the interaction is very reduced because I have no room, no space. And whatever the interaction you will take, it will be typically 1 nanometer range. It's very small. There is no room for, let's say, coupling. So, for affecting the coupling. What was key in the evolution is the possibility to form polymers, and for those polymers to adopt rigid structures, or rather rigid structures, like secondary structures here, the alpha helix or the beta sheet structure of proteins. Why was that important? If you take a molecule like the hemoglobin, there is local rigidity in those segments such that one event occurring, for instance, here will have consequence quite fast at that level. And now the distance between the two sides is not reduced to the, let's say, range of interaction, but has to do with the typical length of this element. And it's already, typically here, 5 nanometers. So there is a way to increase considerably, thanks to such structures, the range of interaction between two sites. Instead of 1 nanometer, you are already here with 5. The marvelous molecule now is typically DNA. DNA is a known hélice. The typical persistence length of a double-strand DNA is 50 nanometer, which means that now I can imagine to have interactions between one side and another one which is distant by 50 nanometer. But you have other structures involving other proteins, such that typically in the genomic DNA, you can have interactions between two sites, typically 1,000 nanometer apart. And they will stick with each other because of interactions with proteins or whatever. So simply because of folding, basically, to make the thing simple, you can overcome the limitations here of 1 nanometer to reach very, very huge distance. And you have a lot of space to put now molecules that will alter, let's say, coupling between sides. And from the evolution point of view, it's very important to be able to alter in very, very different way the way two sides speak with each other by, let's say, interaction with what is in the middle. So these are basically the ingredients. And now the view that I have in mind just to progress is very nicely expressed in this book. If you have some time for Christmas, it's a book that you can read, really, Cell Embryos and Evolution, introducing the hierarchy of biological organization at all scales, from really molecules to almost social organizations. And what you will see is basically that the rules of organization are always the same at any scales, even if the components that are organized are different. And for instance, here you have the acetic acid molecule. When I introduce this molecule to my students and I ask, what do you see? They say, it's a carboxylic acid, and I would say, no, it's not a carboxylic acid. It's a carbonyl group here of ketone, and here it's the OH of alcohols. And they say, no, it's not. And I say, why? It's simply because this part and this part are strongly coupled, giving rise to a new feature, which is carboxylic acid. But it's not trivial by itself. The idea that the physical constants are such that the coupling is strong enough to say that I don't recognize the individual properties of this part and this part, but that I have something new which is emerging. I will come back to this later. here you can imagine to have coupling between two proteins giving rise to totally unexpected behavior. We saw here this effect at that scale. When you have interaction between cells, you have multicellular organisms. This was very important during evolution, and this gave rise to something totally new. And then you have phenomena like symbiosis and whatever that you can observe even at the organism level. So the idea is always this idea that you will have several parts assembling together and giving rise to a new phenomenon and unexpected. So it's an extension of this bricolage évolutif, so evolving toolkit that was introduced by François Jacob, and it's the idea of whatever your community, coupling is more physical, probably assembly more chemical, and symbiosis is a biological word, as a way to imagine the things evolved during biological evolution. But starting from chemistry and maybe before. So what is our, I would say, guideline now with this picture, which is not very precise as you see, but at least it's a starting point, the idea of assembling things and seeing what can arise from assembling. So what is our guideline now, more in the chemistry field? So I will introduce simply this chemical reaction that you may have seen during your studies. It looks like a chemical reaction with molecules, H2, Br2, HBr, but in fact it's not a chemical reaction. It's the result of elementary events occurring in the solution, such that at a given time scale, which is larger than the typical time scale involved in each step, you can describe the evolution in your system as, let's say, accounted by considering that such a reaction occurs in the system. But in fact, it's not a physical reaction occurring in the system. And so we write something that doesn't exist. And this is our picture of complexity at the moment, to account for some abnormal dynamical behaviors observed in, let's say, in biology from a chemical point of view. So the way we see at the moment the thing is that probably, in our view, the complexity of biology in chemical terms has to do from too macroscopic a description of the events occurring in the system. And that it should be much more simpler to go down with, let's say, a more microscopic mechanistic description, and by taking into account the significance of the kinetics of those reactions in order to obtain such a behavior. And from that point of view, this is very close to the approach of statistical mechanics, where you really start from a very microscopic level, and it will become very, very complicated somehow at the macroscopic level of macroscopic thermodynamics, where you have a second principle of thermodynamics, which is not something very easy to catch.
But there, what we want to do is to start from the relevant ensemble and show, for example, that effectively that reaction does occur. For example, with a very fast rate constant.
You mean this one?
Yeah.
At least at my level of chemist, what I would like is basically to say that in order to obtain such a reaction, which could be a goal, let's say, as a dynamic behavior, I can imagine to use those reactions, and now I'm looking for the values of the rate constants such that this collection of reactions can reduce at a given time scale in this one. That would be, it's less ambitious probably, but it's more, let's say, in my culture of chemists. Maybe there is a way to start before, but we proceed really stepwise. And from that point of view, we will see it's the way we proceed. So the idea is that along the way I expressed before, we'll have modules that we will assemble, and we'll try to reduce somehow the behavior of this assembly to something macroscopic, which should be unusual for a chemist. That will be the game. What do we have as modules? We can play with reservoirs of reactants. It's simply to have the free energy source. in relation to engineering, we should favor slow uncatalyzed reaction in order to have plenty of room to introduce catalysis as a way, let's say, to have a nice story to tell. We will have catalysts in that story, and we can also consider molecules as a way to exert a potential on other molecules, to have some interaction. I will give an example. So I will introduce two theoretical propositions, one which is our own, and the other one is connected to molecular motion. So this is one system that we treated not in details, and I'm here also to discuss the details of this model, which has to do with assembling two Michaelis-Menten catalysts, that is, two catalysts obeying the simple cycle that I introduced before. It's something that you will meet everywhere in biology. You have an example here, which is this phosphofructokinase, and you have, in fact, a dimer here. It's not very easy to see, but there is some symmetry. You have one monomer which is here behind, and the other monomer which is here before. And you have two catalytic sites somewhere in the molecule, and what we express here in the model is simply the two catalytic sites, 1 and 2, here, that will incorporate a substrate that will react to form a product. And on one side, we'll have one reaction which is written here, A prime giving B prime, whereas on the other side, we'll have A gives B. And when I say we will reduce to some macroscopic behavior of the things, we will, as chemists, only focus on the reaction we choose as the reaction of interest, AB, and we ignore what happens on the remaining of the molecule. We focus only on one part of the molecule, totally ignoring what happens aside. So we write down all the possibilities of exchanging between the states of, let's say, empty site, a site filled with a reactant, site filled with a product, and so on and so forth. And what we do is to make varying the rate constants of all the chemical reactions in that network. The idea we have is that we want to force with one chemical reaction the catalytic site, the state of the other catalytic site here, by playing with the mechanical coupling I expressed before, which occurs through interactions between the molecular elements here. And in order to force one state with a reaction at the other side, we need to have the reaction at the other side to be very fast. And we'll name it driving. It will be this one. Whereas the other one will experience the state of at the other side, and it's called the slave reaction, which is this one. And what we did was, as a function of the values of the rate constants, to evaluate what was the behavior at the level of a slave reaction. And what we see, as for different, let's say, sets of rate constants, are different phenomena, in fact. For instance, it's possible to transfer free energy from the out of equilibrium reactions occurring at one site here, so with this reaction, to the other one. Here, this is shown here, where you have here the departure from equilibrium for this reaction, which is expressed at 0 when you have no departure, whereas you see the bump here when it departs from equilibrium, and you see that this will occur for given values here of the concentrations here corresponding in fact to given values of the rate constants. If I change those rate constants, and if I penetrate, if I enter into a favorable range of rate constants, I see a totally new phenomenon, which is autocatalysis. That is that the time dependence of the concentration starting from A alone, I will, for this range of value, I can generate a behavior which is totally abnormal, in the sense that it's typically a mono-exponential relaxation, generally for such linear reactions. Here you have something which is clearly non-linear, and for B with the conservation law, it's the same type of behavior. And in fact, it's an autocatalysis, which is absolutely not present in the elementary steps that are written here. And for another range of values, we generate another phenomenon, which is something called the kinetic proofreading, that has to do with, let's say, improving selectivity during chemical reactions. The paradox was addressed by Linus Pauling in the 20s. During the replication of DNA, you have typically 10 to the power 9 bases in DNA, in eukaryotes. And when you evaluate the selectivity among the 4 bases, A, T, C, G, typically you should expect to make 1 error every 10 to the power 3 bases, simply because the interaction during the, let's say, recognition event is not that different between the 4 bases. So normally the level of error should be high. And with 1 error every 10 to the power 3 errors, you can imagine that for 10 to the power 9 bases, at the very end, the level of error should be very, very large. And it's not. So some physicists introduced in the 70s different models to account for this increase of selectivity. And in fact, we have also contained in that model the possibility to increase selectivity much beyond what we should expect on the basis of, let's say, simply changing individually the rate constants. So here, what I want simply to say is that with one typical mechanism, simply by changing the values of the rate constants, we can generate different, let's say, dynamical behaviors that are by far not trivial from the point of view chemistry. And that has somehow to do, I introduced the name genotypes and phenotypes that can be compared somehow with biological phenomena. The other theoretical example I want to give was introduced originally by Pro Hajdari and Jullien in 1997 to account for the motion of some molecules like helicase, for instance, along the DNA. DNA is a molecule that can be seen as a monodimensional polymer, which is polar, that is oriented. It's charged, so it will exert a potential on charged species, which can be different from the one to neutral species. And the components of the models are the following. We have a molecule, which is in that case DNA, that will interact with charged species that way. So you see it's periodic and it's polar. For one state, which will be charged, for instance, and which corresponds to one state of interaction of, for instance, the helicase with DNA, you have some reaction with, for instance, ATP that will change the state of this molecule, changing to, for instance, B, that I consider to be neutral in that case. And now the potential of interaction of DNA for the B state is totally flat here. So imagine that you start at that abscissa, with the molecule being fixed at a given point. You have a random event starting from this charge site to B by a chemical reaction, and so you go to this position. And here you start to diffuse. And you diffuse symmetrically for the lifetime of the B state. And after some time, you will come back to the charged state, and now the polar fact is very, very important. In terms of probability, let's say, of presence or distribution of concentration, you see that there is one part of the molecule that has a probability to go to the neighboring well here, whereas the remaining part will come back to the initial position. And at the very end, you will generate an oriented motion here to the right. We can show that this motion is very selective, depending, let's say, on the geometrical features of the potential, the rate constant, that stuff. The point which is important, again, is that you have a dynamical behavior which is a marvel for a chemist. Oriented molecular motion is something which is not trivial by far, which results from a nice story between a catalyst, which is in fact the object moving. In that case, it's this molecule that will move, a molecular rail, in that case DNA, and a driving reaction which is out of equilibrium. So basically this is the idea that we can see many phenomena as simply arising from coupling systems that are simple from the chemical point of view. So now I just finish by giving the way we think experimentally to implement the story. Because in fact, I'm not a theoretician, I'm an experimentalist. And all what was said before was a sort of frame to progress and to design systems. So what shall we do? Here, and it's even more clear here, to observe a nice phenomena here, I have to fix the values of a rate constant in that system. And unfortunately for me, we have plenty of rate constants. There is no hope almost to engineer that. So, the two strategies we could imagine are the following. Either we have a theoretical work first, with some network, with a topology and rate constants giving rise to a nice dynamical phenomenon, and I engineer a real system working that way. I have problems. The amount of literature dealing with kinetics is very low. So I will have to work myself. It's not rewarding, definitively. And in addition, in relation to literature, I have only a tiny collection of chemical reactions that I can use. Proton exchanges, thanks to Eigen in the 70s, and oligonucleotides also I can play with. These are basically the two sets of chemical reactions I can play with. I play, but it's difficult. There could be, we could imagine another way. Would it be possible to select, in terms of extraction, like an operation of separation in chemistry, not a compound like we do typically in chemistry. We extract, let's say, a molecule from a mixture, but not extracting a molecule, but a network with a given topology and rate constants. The idea should be to target a network and not a compound. The problem is simple. It's a terra incognita for the chemists. There was almost no strategy that were introduced before we started. The advantage, it's not an engineering approach, it's a combinatorial approach. We should imagine to have a mixture of reactants and searching for one exhibiting, let's say, the network with a given topology and rate constant. So it's easier somehow if I can generate a mixture with components exhibiting very different properties, which is something we can do. And in addition, it could be more rewarding because it would be interesting in chemistry to perform very selective separations, and also in biology, maybe, because basically biology is made of networks with given topology and rate constants. So it could be a sort of tool to analyze what biology actually does.
What about the surface? I mean, the surface chemistry, you build these self-assembly monolayers, for instance.
To do what?
Well, when you do it with graphene, which is, I mean, you can actually detach just the graphene sheet afterwards. Or you can make...
But to do what?
Well, for one, okay, so let's take an example where you put down chiral molecules on the surface and create pockets that then guide the reactions and block one of the
you mean
to do catalysis,
to make separations, or
but to not really separations, but to functionalize, I mean, to make a surface hydrophobic or to create catalytic pockets.
That could be done. I don't know whether that could help me in relation to the two things.
That's what I was wondering.
In fact, I'm open, to all the suggestions in relation to solving those problems, and in relation to these goals, basically, I thought only about reactions in volume. We didn't consider too much what could be done on surfaces which could be maybe interesting, but it's
Or
not. Yeah. So it's something we can discuss. But basically, we try to work along both ways. In relation to engineering, I simply said I play with proton exchanges. I also play with light a lot in the group. And here I want simply to show this system not paying attention on structures, to see that there is some analogy with the cycle I introduced with the two sites in exchange. Here it's a combination of photochemistry and proton exchange. Such structures are known to photoisomerize. When you, let's say, shine light on them, you can have a change of geometry to have the two parts here of the molecule on the same side of this bond. And what is nice in that story is that when you do that, there is a change of, let's say, the lability of this OH bond, such that it's much easier to lose a proton here to give this system than from here to go here. And so we can play with light on that direction in order to, if the system is small enough and the intensity of light is strong enough, to fix, in fact, the concentrations in all the species here by light, such that those reactions can be considered as slave reactions. And we will start very soon to apply the trick of driving reactions and slave reactions that I expressed before. This is the only system we can really engineer at the moment in the group, because we know all the rate constants, we measured them, and we know a lot about the photophysics of that system. But it's So just a few words about the other strategy. The idea is to see whether we can design a strategy to sort from a mixture, a chemical network with a given topology and given values of rate constants. So our view is simply that separation will be a motion, so we need a field and a reaction, in that case a chemical network. To reveal kinetics, what you use is the trick of Debye, Huygens, and the others, to apply periodic fields on the system and change the frequency in order to be able to address different, let's say, dynamics in the system. So this is typically what we studied up to now. So we can, for instance, have a constant field, but which is periodic in space. This is typically the model of Brownian motors that we saw. And in that case, we saw that it opens the way to oriented motion. We show also that it was possible by adding to this modulation in space to add a modulation in time. Again, we obtain an oriented motion theoretically. All this work is theoretical, but with much less constraints in terms of experimental implementation, because this point is important. You can have a uniform field, no period in space, but now period in time, and now there is no oriented motion, there is a selectively enhanced diffusion, dispersion, something we discussed with Axel and Raphael yesterday. And we started in 2005 and we continue. We showed also that when you have a time periodic field plus a phase-related temperature modulation acting on the dynamics of a chemical process with some phase relationship, I will just introduce briefly that, we can gain some oriented motion. And the type of story is the following. When you have a chemical reaction and when you change the temperature, you change the values of the rate constants here. As a consequence, the concentration here will evolve with a first order term here containing an in-phase term and an out-of-phase term. And what is interesting for us is that this out-of-phase term exhibits a sort of resonance in the space of a rate constant. In fact, just to explain briefly what happens here for the in-phase term, in order to have a response to the temperature modulation which has a large amplitude, you need to have the same amount of A and B in order that the change of temperature will reveal by a large change of concentration. which fix the fact that the response is maximized along this diagonal corresponding to the equilibrium constant equal to 1 here. And when the reaction is very, very fast, you are in phase with the temperature modulation, so the amplitude of the response is maximal, whereas it's 0 when the reaction is very, very slow here. And for the out of phase component here, basically still the response is maximized here along the diagonal, but you kill the fast components here simply because they respond in phase. And so the out of phase term here is maximized only for, let's say, one resonance species exhibiting this type of relation. And this can be generalized for larger linear networks. So the idea is to use the fact that you have a resonance for a given compound exhibiting given values of rate constants here. And so if you have a mixture, typically when you observe the system, you will have a response which is a sum of all the responses here. And it may be that you are interested in this component, which has a tiny response here. So the idea is simply to add a modulation, a sort of lock-in amplification of the system. You have always the zeroth order response you are not interested in here, but you want to maximize the modulated response originating from the compound you are interested in here. So the idea is now how can one kill this while revealing the phase and introducing the motion. So the idea is simple. You have a modulation of temperature. For the motion, you need the field. We modulate the field at the same frequency. Then you have a phase you can play with. And the idea is to apply both an electric field which is modulated, in that case around a 0 value, modulation of the temperature. And now what you gain in that case is that the molecules will move with an oriented motion, which again exhibit some resonance phenomenon now for this phase relation between the temperature and the field, and again for a given value of the rate constant. So it's the idea that we can play that game. And just to finish, experimentally we use microsystems to perform those experiments because it's much easier to control really all the parameters, fields, temperatures, and also to see what we do simply with a microscope to observe the phenomena. So the technology is somehow simple. We simply use a sort of oven to cook, in fact, such systems based on molds, in fact, that we design, and we work somehow quite a lot with that. So with electric field, we can play along two directions. I don't want to enter into the details. And what you see here, for instance, is that we introduce some fluorescent molecule by this injection channel. And we can play with electric fields, either to have a molecule moving, or to have some angle, or to have some zigzag phenomenon, and this can be done quite easily, and we can also modulate temperature in this system. So we learned how to treat the data. In order to modulate the temperature, we use resistors, and you have here a small system, which is an ITO plate, a semiconductor, on which we deposit gold electrodes. And you can hit locally the system and modulate the temperature quite locally. You see the scale here. We have systems to measure temperature and that stuff. And we are at the point to validate, in fact, to evaluate, but I think we will validate what I showed before in order, in fact, to be able to generate the oriented motion in the system, and so to sort from a mixture the system we target. So just to conclude, to have for you a feeling about what that means for chemists to address this border, clearly, and I cannot do them by myself, we need theory, a lot of theory, definitively. Along the way, which assemblies to generate which dynamical behavior. We have also questions related to the way to put the equations, whether we should adopt some continuous description of concentrations, or shall we really incorporate space and that stuff. It's really, we have plenty of questions. We have synthesis, we have to collect kinetic data, and you saw that you have analysis and separation tools. So just to conclude, the historical perspective to motivate the work, chemistry started in, let's say, in the organic chemistry with Friedrich Wöhler, we saw, and in 30 years we were able to see the emergence of organic chemistry that was really coupled to natural products, that was linked to fatty acids at that time. It was the possibility to reproduce with the chemical tools natural molecules. And there was some connection. We find again that connection between biology and chemistry